The next topic that we need to address is pulse shaping, and the objective, in order to actually finish our digital communication transmitter chain. So the objective of pulse shaping is to manage communication over channel with finite bandwidth. We call that band limited channel. And the reason that we need that is that sudden changes in time domain signals results in very high frequency in the frequency domain. And where does this happen? Remember that our bits or symbols are generally represented by a sudden rise to a value and then sudden fall to another value, right? Which is what we call the square, which is the square pulse shape that we deal with in the digital domain. Now the problem is that this in time results in what we remember as the sinc function in frequency, right? This is in frequency. But the sinc function never finishes, right? It keeps on having values even when you reach infinite frequency. Now the problem is this will not happen because our channel is gonna have some limited band. So it's gonna cut the signal. So you end up in frequency domain with a signal that looks like this, and then it finishes, right? Now a signal that looks like this in frequency, which is going to be imposed by the fact that our channel is band limited, that's the channel bandwidth, and after that any higher frequencies are not going to go through the channel will not allow them to go through, will make them disappear. Then this reflects back in our time domain, and our square pulse that we used to have in our time domain is going to look like this. And then it will be, this is the time domain coming from this effect, right? This was supposed to be the ideal case. This is the ideal case if the channel allows everything to go through it. But the non-ideal or the practical, this is the practical case. Okay, so this is ideal, this is practical case. The practical case is that the channel is gonna stop frequencies higher than a certain value, and accordingly it's gonna cause what we call time spreading. Okay, so your signal in time domain is no longer just a square, it's going to be spread across time. And now imagine you send a certain bit value followed by another bit value followed by a third bit value, right? And each one of those is gonna be spread around like this, right? So what happens is what we call inter-symbol interference. So that's ISI. So basically bits overlap with each other, causing errors in detection, of course, right? So band limited communication causes inter-symbol interference, and I've described to you now how the effect happens. It limits the frequency domain representation of your bits, causing the time domain representations to spread around, and accordingly the bits interfere with each other, and we call that inter-symbol interference. Now, in order to avoid that, rather than using the square pulse shape, so to avoid, solution for that, to avoid ISI, we use other shapes, pulse shapes, different from the square shape. So basically the square shape is no good, right? So what's the suggestion? Nyquist has defined Nyquist pulse shaping criteria 1. Nyquist has defined several criteria or several ways that you can use to basically achieve avoiding intersymbol interference. Now the criteria one says that your pulse shape satisfies two things. Number one, two conditions together. The first condition is that limited bandwidth in frequency, and the second thing is that your pulse shape P of t and the second thing is that P of t is equal to some value at t equals 0, and it's equal to 0 at t equals plus or minus n tb. Okay, for n belongs to 1, 2, 3 up to infinity, right? So what does this mean? So in frequency domain, this means that when you look at your signal, at your pulse, the Fourier transform of your pulse should be something that finishes at certain point, right? Should be something like this, or something like this, or something like this, or whatever the shape. The important thing is that it has a start and an end for its existence. Does not exist across all frequencies, right? And then the second condition says that your pulse at the center point should have some value at all other repetitions of TB. So right, it should have a 0 value. So 0, 0, 0 here, a 1 here. So for example, something that looks like this, let's say, will satisfy such, right? It just has to be non-zero here, and it has to be 0 here, 0 here, 0 here, 0 here, 0 here, and it doesn't matter what's the value in between. These values can be anything, right? Doesn't matter. What matters are only the solid points. They all have to be equal to 0, except this one has to be equal to some non-zero value, positive non-zero value, right? This is in time domain. So there is a condition in frequency domain, there is a condition in time domain. Now, one pulse that was found to satisfy this is basically in frequency domain, the square pulse, right? Okay, which has a certain bandwidth B in frequency domain, and this one corresponds in time domain to the sinc function, right? Right, and that sinc function is chosen such that it's equal to 0 at TB, at 2 TB, at 3 TB, and so on, right? So accordingly, this is gonna define exactly what's the bandwidth in this case of this signal. It's gonna be exactly a function of TB, right? From the relation between the sinc and the square function. So this is called the sinc pulse shape, or Nyquist first criteria pulse shape. Now in actual practical systems, you cannot have something with infinite time extension, because this is not practically possible. So you end up with this stopping at one point, which means that in frequency domain it will have some frequency leakages, but they are very small and negligible, right? So practically you end up with a truncated sync pulse shape, and accordingly you end up with in frequency domain some leakages. Okay, which is due to truncation. Okay, that's it for pulse shaping. The kind of questions that you can get in this case is that just find pulse shape for 3 megabits per second, okay, transmission system. So in that case, you know that the bits per second, you have 3 times 10 to the power 6 bits per second, and accordingly TB is equal to 1 over 3 times 10 to the power 6, right, seconds. And accordingly you figure out that the pulse shape is going to be a sync function that is equal to 0 at 1 over 3 times 10 to the power 6, 1, 2 over 3 times 10 to the power 6, and so on. And frequency domain, it's going to have a bandwidth which is 3 times 10 to the power 6 hertz, right? That's basically the frequency domain representation and the time domain representation. Now you need to find the correct sync expression that satisfies this, and it's known because these intersections are a function of the parameters of the sync function. So if you look at the sync function, you will figure exactly a sync that goes to 0 at that point is given by sync such. Okay, so just need to find the correct expression.